There is a wiring diagram inside a cell. It is vast, it is ancient, and it is electric.
It really is.
And before we can even begin to talk about how, opioids kill pain, or how beta blockers slow the heart, or how antidepressants can lift a mood, we have to look at the cables themselves. Because drugs, no matter how advanced they are, they don't create new functions. They don't invent new physiology. They are hackers. They hijack, they mimic, or they block the existing communication lines that your body has been using for millions of years.
That is the fundamental truth of pharmacology. You're essentially throwing a wrench, or maybe a lubricant, into a machine that is already running. And if you don't understand the machine...
you can't understand the intervention.
Exactly. You're just guessing.
And that is our specific mission for this deep dive. We are stripping the house down to the studs. We are looking at a neurotransmission wiring the nervous system.
The absolute bedrock.
And to do this properly, to really get the signal from the noise, we are synthesizing the two absolute titans of the field. We have Chapter 6 of Capsong and Trevor's Basic and Clinical Pharmacology, and we have Chapter 8 of Goodman and Gilman's The Pharmacological Basis of Therapeutics.
You have to use both for this topic. They're like the Old and New Testament of pharmacology.
How so? What's the different flavor they each bring?
Capsong is just phenomenal at the clinical scaffolding. The what goes where, the organizational clarity. It gives you the map of the autonomic nervous system. It's clean.
Okay, the blueprint.
Right. But Goodman and Gilman, that is the engine room. That gives us the molecular reasoning, the thermodynamics of vesicle fusion, the deep signaling cascades. It's the why.
So Katzin tells us the car turns left. Goodman and Gilman explains how the differential gear actually works.
That's a perfect way to put it.
And I want to be really clear right up front. This is an interpretive synthesis. We are building a conceptual map to prepare your mind for the reading. We are not a substitute for the chapters.
Oh, absolutely not. You still have to do the work.
Please, do the work.
Think of this as the orientation before the expedition. We want you to understand the logic of the system, so that when you stare at those dense diagrams of catecholamine synthesis, you don't just see a list of enzymes, you see a narrative.
And the narrative arc today is fascinating because it's all about control. But it's not the kind of control we're used to in, say, engineering with simple on-off switches.
No, not at all.
The metaphor that kept jumping out at me from the reading is that biological control depends on balance, not force. It's about modulation.
It's a mixing board, not a light switch. You have gain, you have fade, you have feedback loops. It's subtle.
And today we are going to break that board down. We'll start with the macro architecture, the difference between the voluntary and involuntary wiring. Then we're going to zoom way in to the molecular level, the synapse, and look at the two great chemical languages, cholinergic and adrenergic.
And finally, and this is crucial, we have to talk about how the system fights back. Because when you introduce a drug, the body doesn't just take a lying down.
It pushes back. It adapts.
That's the whole concept of homeostasis and tone. It's why pharmacology is so difficult and why a drug that works perfectly on paper might fail spectacularly in a patient.
Okay, let's start with the architecture. Section 1, the architecture of control. We have the central nervous system, brain and spine, and then the peripheral nervous system, which is everything else.
Right.
But the real divide, the one that matters for us today, is between the somatic and the autonomic.
This is the first, most important fork in the road. The somatic system is the part of you that interacts with the outside world, consciously.
It's me deciding to reach for this glass of water.
Exactly. It deals with posture, movement, even respiration to some degree. It's your voluntary nervous system.
And the autonomic.
Well, autonomic means autonomous. It's vegetative. It's the operating system running in the background that you never have to think about.
Thank goodness.
It manages your internal environment, blood pressure, digestion, heart rate, temperature, all of it, independent of your conscious will. If you had to consciously regulate your vascular resistance every time you stood up,
you'd faint before you could even finish the thought.
You'd be on the floor.
Now, in Katzung, there's this great diagram that highlights a crucial anatomical difference between these two. It's not just a functional difference, the actual wiring is different.
Totally different.
The somatic system is a direct line.
Right. It's a marvel of speed and precision. You have a single motor neuron located in the CNS, in the spinal cord. It shoots one long, heavily myelinated axon straight to the skeletal muscle.
No stops, no layovers.
None. It's an express train. It releases its chemical, acetylcholine, the muscle contracts. Done. Simple, fast, direct.
But the autonomic system, our sympathetic and parasympathetic divisions, it's a two-neuron relay.
It is. You have a preganglionic neuron that leaves the spine, but it doesn't go all the way to the target. It stops at a station. A ganglion, which is basically just a cluster of nerve cell bodies outside the CNS. So the first neuron passes the baton to a second neuron, the postganglionic neuron, and that one travels the rest of the way to the heart or the gut or the pupil.
I was looking at this and thinking about efficiency. Why the extra step? Nature usually hates redundancy. If the somatic system works so well with the direct line, why does the autonomic system introduce a middleman? That seems to imply latency, a delay.
It does.
So what is the biological payoff for that relay station?
That is the crucial question. And the payoff is amplification and diffusion. In the somatic system, you want precision. You want to twitch this finger, not the one next to it.
One neuron, one muscle fiber group.
Exactly. But in the autonomic system, specifically the sympathetic division, you often need a system-wide alert. A single preganglionic fiber can enter a ganglion and branch out to contact many postganglionic fibers.
So it's not a simple relay, it's a broadcast tower.
It's a broadcast tower. It turns a whisper into a shout. If you see a predator, you don't want to micromanage your response. You don't want to say, okay, heart, speed up. Okay, pupils, dilate.
No, you want it all to happen now.
You want to dilate your pupils, accelerate your heart, shunt blood from your gut to your legs, and mobilize glucose all at the very same time. The ganglionic architecture allows for that massive divergence of the signal.
That makes the relay make so much more sense. It's not a stop, it's a distribution hub.
That's it.
Now, within this autonomic system, we have the two famous divisions, sympathetic and parasympathetic.
The yin and yang of physiology. The gas pedal and the brake.
Let's look at the sympathetic first. Ketsom refers to this as the thoracolumbar outflow,
which is just anatomical coordinates. It's a fancy way of saying the nerves emerge from the thoracic and lumbar segments of the spinal cord.
The middle of the back.
The middle of the back. And this is your fight or flight system. In the older literature, it was called the ergotropic system, meaning it leads to energy expenditure.
And structurally, this supports that broadcast idea we just discussed. The preganglionic fibers are short. They exit the spine and almost immediately hit these chains of ganglia running alongside the backbone.
Right, the paravertebral ganglia.
Yeah.
Because the ganglia are so central and close to the spine, the postganglionic fibers have to be really long to reach the organs out in the periphery.
And that centralized setup facilitates that big synchronized discharge we were talking about.
Exactly. It's built for coordinated action.
Now, there is one part of the sympathetic system that completely breaks the rules, and G&G spends some time on this because it's a pharmacological goldmine. The adrenal medulla.
Oh, the adrenal medulla is a fascinating evolutionary quirk. If you look at it embryologically, the cells of the adrenal medulla are actually modified sympathetic ganglion cells.
What does that mean, a modified?
They are, for all intents and purposes, neurons that forgot how to grow axons. They never grew the wire.
So instead of a two-neuron chain, it's a one-neuron chain leading to a gland.
Effectively, yes. The preganglionic fiber travels all the way from the spinal cord to the adrenal gland, which sits on top of the kidney. It releases acetylcholine on these modified cells. But because these cells don't have wires reaching out to target organs,
They just dump their chemicals into the bloodstream?
they dump their neurotransmitter epinephrine and norepinephrine directly into the bloodstream. They turn the neural signal into a hormonal signal.
Which is brilliant.
It is brilliant. It ensures that the fight or flight message reaches cells that aren't even wired to the nervous system. Every single cell with a blood supply gets the memo that we're in danger. It's the ultimate broadcast.
Okay, so contrasting that, we have the parasympathetic division, the rest and digest system.
Or trophotropic, leading to
Yeah.
growth, digestion, and energy storage. This is the craniosacral outflow.
Meaning the nerves come from the cranial nerves at the top, specifically the third, 7, 9X, and the big one, the vagus nerve X,
Wandra.
and the sacrospinal cord at the very bottom. Why is the brake pedal split between the head and the tail? It seems like an odd design.
It's largely about protecting the vital inputs and outputs. The cranial nerves handle the head, neck, and, via the vagus, the thoracic and abdominal viscera, all the core stuff.
And the sacral nerves?
The sacral nerves handle the plumbing, the bladder, the rectum, and the reproductive organs. Structurally, it's the complete inverse of the sympathetic system. You have these long preganglionic fibers that go all the way to the organ.
And the ganglia are located right next to or even inside the organ walls.
They're embedded in there, which means the postganglionic fibers are tiny.
Microscopic sometimes.
Right. And this architecture dictates function. It allows for discrete, localized control. You can digest your lunch without slowing your heart rate. You can constrict your pupil without emptying your bladder.
It's not an all-or-nothing system.
No, it is a system of specific targeted reflexes, which is the complete opposite of that all-out nature of the sympathetic discharge.
I want to pause on a really interesting update from the Katsung text regarding the anatomy. They mentioned something they call a sacral outflow revision.
Ah, yes. This is a great example of how molecular biology is rewriting anatomy textbooks that have been static for a century.
What's the change?
For 100 years, we taught that the sacral outflow, the nerves controlling the bladder and bowel, was parasympathetic.
Yeah.
It comes from the right place, it uses the right chemical, but recent genetic tracing, it shows that the transcription factors in those neurons, the genetic code that tells a cell what to become, it looks distinctively sympathetic.
Wait, so you're telling me the nerves that empty the bladder might actually be sympathetic in their origin, even if they act parasympathetic?
Embryologically, yes. Their lineage is different. Even though functionally they use acetylcholine and do rest and digest things, they come from a different family tree. It completely challenges that clean craniosacral definition.
So we might have to change the textbooks.
We might be moving toward calling it the cranial autonomic and spinal autonomic systems. It's just a reminder that nature doesn't really care about our clean classifications.
Speaking of classifications that don't fit, we have to talk about the third division. The one that often gets treated as a footnote, but is actually, it's massive. Yeah. The enteric nervous system, the ENS.
The brain and the gut. And calling it a footnote is just, it's unfair. We are talking about 100 to 150 million neurons lining the walls of your GI tract.
That's more neurons than in the entire spinal cord.
More than the spinal cord. And G&G emphasizes that this isn't just some dumb relay station for the brain. It is semi-autonomous.
It has a mind of its own.
It is fully capable of running the show on its own. If you sever the vagus nerve, completely cutting the connection to the brain, the gut will keep functioning.
Really?
Absolutely. It will continue peristalsis. It will continue secretion. It won't be as coordinated or, responsive to stress. But the basic machinery keeps running.
How is that even possible?
It has its own reflex arcs. Right. It has sensory neurons that taste the chemical composition of the food. It has interneurons that process that data. And it has motor neurons that tell the muscle to contract.
A self-contained circuit.
Completely. And it uses a staggering array of neurotransmitters. We usually think of serotonin as a brain chemical for mood, but something like 90% of the body's serotonin is actually in the gut.
So when we take an SSRI antidepressant and we get GI side effects like nausea or diarrhea.
That's why. It's because you are messing with the signaling of the enteric nervous system. It's this complex, highly integrated neural network that just happens to be wrapped around your colon instead of inside your skull.
Okay, so we've mapped the highways. We have the somatic express lane, the sympathetic broadcast network, the parasympathetic local roads, and this autonomous city-state of the enteric system.
A good map.
Now let's zoom in. A road is useless if nothing is moving on it. We need to look at the cargo. We're moving to section 2, the synapse, the unit of action.
This is where pharmacology stops being abstract and starts being mechanical. The synapse is the junction, that tiny gap between the nerve terminal and the effector cell. And the entire game here is the life cycle of the neurotransmitter.
And we have 5 distinct steps in this life cycle: synthesis, storage, release, binding, and termination.
That's the sequence.
If you are listening to this, you should visualize these steps as points on a factory assembly line, because every single drug we talk about for the rest of this series is essentially sabotaging one of these 5 machines.
That's the framework. And let's use the cholinergic system, which uses acetylcholine, or AAC, as our model to walk through this. This is the language of the parasympathetic system and also the somatic motor nerves.
Okay, step 1, synthesis. We need to make the acetylcholine.
Right. Synthesis happens right there in the nerve terminal. The recipe is actually pretty simple. You take choline and you add acetyl-CoA.
Okay.
There's an enzyme, choline acetyltransferase, or CHAT, that stitches them together, but there's a logistical problem right from the start.
Which is what? The cell can't make choline?
Correct. Choline is a large charged molecule. It doesn't just drift through the lipid membrane of the cell. It has to be actively pumped in from the extracellular fluid.
And this pump is the bottleneck.
It is the rate-limiting step for the whole process. It's called a sodium-dependent choline transporter, or CHT. The speed of this pump determines how much OTH you can make, period.
And I'm guessing we can hack this.
Oh, of course. There's a research drug called hemagglutinium. It doesn't do anything else. It just blocks the CHT. If you give this, The nerve fires a few times, uses up its existing supply of HE, and then it fails.
It runs out of bullets.
It's like cutting the supply line to a factory. The machinery is fine, but there are no raw materials coming in the door.
Okay, so that's synthesis. Step 2, storage. We've made the HE. Now what?
You can't just leave neurotransmitters floating around in the cytoplasm. For one, they're liable to be broken down, and for another, they aren't concentrated enough for a big burst release. So the cell packs them into vesicles.
Little molecular grenades ready to go.
That's a great way to think of it. And this packing requires energy. There's another transporter called VAT, the vesicle-associated transporter. It uses a proton gradient to shove HE into the vesicle, concentrating it.
So can we sabotage the loading dock?
We can. With a drug called vesamical, it blocks the VAT. So synthesis happens, the vesicles are all lined up, but they're empty. When the nerve fires, the vesicles fuse with the membrane, but nothing comes out.
It's shooting blanks.
Exactly.
All right, step 3, release. This is the most complex and honestly the most beautiful part of the process. Goodman and Gilman really goes deep into the molecular biophysics here. It's not just the bubble pops.
Oh no, it is a high-stakes thermodynamic battle. You have the vesicle membrane and the nerve cell membrane. Both are made of lipids. They repel each other. They do not want to touch.
Like 2 water droplets.
Precisely. To get them to fuse, you need to overcome that hydration barrier. You need to force them together.
Enter the snares.
The snare complex. This is a family of proteins that act like a molecular winch. You have V snares on the vesicle. The main one is called synaptobrevin. And you have T snares on the target membrane. Those are syntaxin and SNAP25.
I'm picturing them like the ropes on a drawbridge just hanging there.
Or a zipper that's half done. And then the action potential hits the terminal. That opens voltage-gated calcium channels. Calcium rushes into the cell. That is the trigger.
The spark.
The spark. Calcium binds to a sensor protein on the vesicle called synaptotagmin. This binding causes the snares to suddenly twist together, coiling up incredibly tightly. This coiling exerts a tremendous physical force.
It literally pulls the 2 membranes together.
It drags them together until they merge and the contents are dumped into the synapse instantly.
This mechanism, this molecular zipper, is the target of one of the most potent toxins known to man, botulinum toxin.
Botox. It is a protease, a tiny molecular pair of scissors. It gets taken up specifically into the cholinergic nerve terminal. Once inside, it seeks out those snare proteins, specifically SNAP25 or synaptobrevin, and it just snips them.
So the zipper is broken, the winch cable is cut.
It's destroyed. The vesicles are full of HE, the calcium signal arrives, everything is ready to go, but the fusion machinery itself is severed. The vesicle cannot release its payload. The result is flaccid paralysis. The muscle simply stops receiving orders.
It's incredible to think that we use this for cosmetic wrinkles or for treating something like blepharospasm, that uncontrolled eyelid closure.
We are inducing a localized molecular failure of exocytosis to relax a muscle. And you can compare that to the venom of the black widow spider lytrotoxin. It does the opposite.
How so?
It creates pores in the nerve terminal membrane that just let calcium flood in, completely uncontrolled, without any action potential.
So it bypasses the entire electrical trigger system.
Completely. The calcium levels skyrocket, the snares are forced to fuse over and over, and you get an explosive convulsive release of all the vesicles at once.
Leading to massive contraction, cramping, pain.
Followed by paralysis because you've completely exhausted the supply of neurotransmitters.
2 ways to kill the signal. Lock the door with Botox or blow the door clean off with latrotoxin. Okay, step 4 is binding, which we will handle in the receptor section. So let's jump to step 5, termination. You've sent the signal, now you need to hang up the phone. How does the cholinergic system stop the noise?
It uses enzymatic destruction. This is a key feature of acetylcholine. There's an enzyme called acetylcholinesterase, or ACE, that's tethered right there in the synaptic cleft, waiting. And it is one of the most efficient enzymes in all of biology.
How fast are we talking?
We're talking diffusion limited. It can cleave thousands of molecules of ATs per second. As soon as AC binds to its receptor and pops off, AC is there to chop it into choline and acetate, ending the signal.
Which ensures that one nerve impulse produces exactly one muscle twitch. No echoes.
No echoes. It's a clean digital signal. And this, of course, is a major drug target.
Huge.
If you block this enzyme with an acetylcholinesterase inhibitor like the drug neostigmine or the nerve gas sarin, you prevent that breakdown. The AT builds up in the synapse, it binds, pops off, and binds again and again.
You get a massive amplification of the signal.
A massive amplification. In a disease like myasthenia gravis, where the receptors are failing, this can be therapeutic. In nerve gas poisoning, it causes a fatal system-wide spasm.
So that's the cholinergic life cycle. Import choline, synthesize, pack in vesicles, calcium trigger, snare zipper, release, and then the enzyme chop.
A perfect summary. That's the whole story.
Okay, but now we have to look at the other side of the coin, section 3, adrenergic transmission, the sympathetic language, norepinephrine. The steps are similar, but the details and the drug targets are totally different.
They really are. The main difference starts right at synthesis. It's a longer assembly line. We start with the amino acid tyrosine. An enzyme, tyrosine hydroxylase, converts it to dopa. This is the rate-limiting step.
Sure, we can block that.
We can, with a drug called metarosine. Then the dopa is converted to dopamine.
And here's a weird quirk G&G points out. The conversion of dopamine to norepinephrine happens inside the vesicle.
It does. For ASHET, the finished product is loaded. For NE, the precursor dopamine is loaded into the vesicle, and the final synthesis step happens in the truck, so to speak.
Talk to me about the loading mechanism here. It's not the VAT transporter.
No, this one is called VMAT, the vesicular monoamine transporter. And it's a bit more promiscuous. It will move dopamine, serotonin, norepinephrine, even histamine into vesicles.
And we have a famous drug that hacks this step, reserpine.
Reserpine, a drug with a really fascinating and somewhat dark history. It was one of the first effective antihypertensives. It binds tightly to the VNAT and irreversibly blocks it.
So the dopamine is made in the cytoplasm, but it can't get into the vesicle to be converted and stored?
Correct. And the cytoplasm is a hostile environment for it. There are mitochondria floating around that are full of an enzyme called monoamine oxidase, MAO. The MAO just sees this free-floating dopamine and chews it up.
So the nerve is effectively stripped of all its ammunition.
That's what we call a chemical sympathectomy. You are depleting the nerve terminals of their transmitter. The nerve creates an action potential. The calcium comes in, the vesicles fuse, but they are empty.
Which would lower blood pressure.
Very effectively. But because it also depletes these same chemicals in the brain, it can cause profound suicidal depression. It's a powerful but blunt instrument.
Now, you said the biggest difference between the two systems is termination. Acetylcholine gets chopped up by an enzyme. What happens to norepinephrine?
The adrenergic system is, well, it's more eco-friendly. It recycles. It relies on reuptake.
The vacuum cleaner?
The vacuum cleaner. It's a protein called the norepinephrine transporter, or NET. It sits on the presynaptic membrane, and its whole job is to suck the NE back out of the synapse to be stored and used again. We call this uptake 1.
And this is where the mechanism of a drug like cocaine becomes crystal clear.
This is exactly what cocaine does. It is a potent inhibitor of the NET. It jams the vacuum cleaner. So the nerve releases NE, but the NET can't clear it from the synapse. The NE just lingers.
Bouncing around, stimulating the receptors over and over again.
Over and over. So the euphoria, the tachycardia, the hypertension, it's all just unterminated sympathetic signal. It's not that cocaine stimulates the receptor directly, it just prevents the off switch from working.
And tricyclic antidepressants do something similar?
They do, though with less potency and different kinetics. But it's the same principle. Block reuptake, increase synaptic concentration.
And just to close the loop on termination, there are enzymes too, right? MAO and COMT?
Yes, but there's secondary players in the synapse. MAO, as we said, handles the leaked transmitter inside the cell. And COMT, catecholomethyltransferase, mostly handles circulating catecholamines in the liver and other tissues. But for the immediate second-to-second termination of a nerve signal, reuptake is king.
Okay, section 4, receptors and signaling. This is where we need to get into the Goodman and Gilman weeds. It's not enough to say it binds. We need to know what happens inside the cell after it binds.
This is the transduction phase. The neurotransmitter is just a key, the receptor is the lock. But turning the lock triggers a whole Rube Goldberg machine inside the cell.
Let's start with the cholinergic receptors. We have two main families, nicotinic and muscarinic.
And they're named after the alkaloids that were first used to tell them apart. Nicotine from tobacco and muscarine from poisonous mushrooms. The real difference between them is speed versus complexity.
Nicotinic receptors are ion channels.
They are ligand-gated ion channels. It's a physical pore made of protein subunits. H binds, the pore snaps open, and sodium ions rush in.
It's a direct electrical effect.
It is immediate depolarization. We're talking milliseconds. This is why you find them at the neuromuscular junction. When you want to sprint, you don't want to wait for a biochemical cascade. You want fire and you want it now.
But muscarinic receptors are different. They are GPCRs-G protein coupled receptors. And this is where the listeners need to pay attention to the letters. GS, G, G, Q.
This is the alphabet of cellular control. Muscarinic receptors come in subtypes, M1 through M5. The important ones are M1, M2, and M3. And M1 and M3 are coupled to a G protein called GQ.
Okay, walk us through the GQ pathway. What does it do?
A sheet binds to an M3 receptor. The GQ protein then activates an enzyme called phospholipase C. This enzyme takes a lipid that's just sitting in the membrane and splits it into two new signals, IP3 and DAG.
And IP3 does what?
IP3 floats over to the endoplasmic reticulum, the cell's internal calcium storage tank, and basically unlocks the calcium vault.
Calcium floods the cell.
Calcium floods the cell. And in a smooth muscle cell, calcium causes contraction. In a gland, calcium causes secretion. So M3 activation is why the gut squeezes and the salivary glands spit.
But M2 is different. It's on the heart.
Right. M2 is coupled to G. And the I is for inhibitory. When HE binds to M2 on the heart, the JAG protein does two things. It inhibits the production of a messenger called CAMP, and it directly opens potassium channels.
So potassium flows out of the cell.
It flows out, taking its positive charge with it.
Yeah.
This hyperpolarizes the cell, making it harder to fire an action potential. It slows the heart rate.
So the exact same molecule, acetylcholine, causes the gut to contract using GQ and calcium, and the heart to relax using G and potassium.
Precisely. The meaning of the message is defined by the listener, not the speaker. It's all about which receptor is there and what machinery it's hooked up to.
Okay, now the adrenergic receptors, alpha and beta, all GPCRs.
All GPCR, so let's decode them. Alpha-1 receptors are GQ coupled, just like M3 muscarinic receptors.
So they also mobilize calcium.
They do. And these are found all over the smooth muscle of blood vessels. So norepinephrine hits alpha-1, you get a GQ signal, calcium release, and the smooth muscle contracts.
It squeezes the vessels and raises blood pressure.
That's it.
And alpha-2.
Alpha-2 is coupled to G, just like M2. It inhibits. But here is the really cool twist. Alpha-2 receptors are usually presynaptic. They live on the very same nerve terminal that is releasing the norepinephrine.
It's an autoreceptor, a self-receptor.
It's a negative feedback loop.
Yeah.
When the nerve gets overexcited and releases a massive amount of NE, some of that NE floats back and hits the alpha-2 receptor on the nerve itself. The G protein then shuts down the calcium channels in the terminal, stopping any further release.
It's the, okay, shut up, you're shouting receptor.
That's a perfect description. It's a crucial mechanism for preventing the system from burning itself out.
And we have drugs like clonidine that target this.
Exactly. Clonidine is an alpha-2 agonist. It stimulates these receptors. It basically tricks the brain into thinking sympathetic activity is way too high, so the brain shuts down the outflow from the CNS. It lowers blood pressure by hacking the feedback loop.
Okay, finally, the betas, beta 1 and beta 2.
Both of these are coupled to Gs. The S is for stimulatory. They both activate an enzyme called adenyl cyclase, which then makes a ton of the second messenger, CAMP.
But wait, if they both use Gs and they both make CAMP, why does beta 1 activation speed up and strengthen the heart, while beta 2 activation relaxes the smooth muscle in the lungs?
That is the magic of tissue-specific machinery. In the heart, which is full of beta 1 receptors, CAMP activates kinoses that phosphorylate calcium channels, which lets more calcium in. More calcium equals a stronger, faster beat. But in the smooth muscle of the bronchioles or blood vessels, which have beta 2 receptors, that very same CAMP messenger actually inhibits the machinery of contraction. It inhibits an enzyme called myosin light chain kinase.
So in the lung, more CMP leads to relaxation and bronchodilation.
That is wild, isn't it? The same second messenger, CMP, has opposite mechanical effects depending on the cell type it's in.
It's all context-dependent coding.
It is.
Section 5, co-transmission and modulation. We've been presenting this as a pretty binary choice. A nerve is either cholinergic or it's adrenergic. But both Katsung and G&G say this is a clean signal myth.
It's the one neuron, one transmitter dogma, and it is dead. It was a useful simplification, but it's wrong. Real neurons release a cocktail of chemicals.
So a sympathetic nerve doesn't just spit out norepinephrine.
Not at all. It also releases ATP. It releases neuropeptide Y, or NPY.
Hello.
A parasympathetic nerve releases ASHI, but also things like vasoactive intestinal peptide, or VIP.
Why? I mean, what is the advantage of the cocktail over a single clean signal?
Nuance and temporal resolution. G&G gives a beautiful example of the sympathetic nerves that feed the vas deferens, the smooth muscle tube involved in ejaculation. It needs a very complex contraction profile.
Right. So walk us through the sequence of that cocktail.
When the nerve fires, the first thing to hit the muscle is a burst of ATP. ATP acts on P2X receptors, which are ligand-gated ion channels, just like nicotinic receptors.
Super fast.
Super fast. It causes a rapid electric twitch, a staccato effect. That's the fast attack.
Okay.
Then A few milliseconds later, the norepinephrine hits the alpha-1 receptors. We know that's GQ coupled. It takes a second to build up the calcium, but it creates a strong, sustained contraction. That's the melody.
And the NPY, the neuropeptide.
Neuropeptide Y acts on even slower GPCRs to modulate calcium handling over minutes, preventing the muscle from fatiguing and maintaining tone. It provides the long, slow background harmony.
So you have a fast twitch, a strong squeeze, and a long-lasting modulation, all from one nerve firing.
All from one signal packet. And this explains why some drugs act partially, or why physiological responses are so robust. You have backup signals. If you block one, the others can still have an effect.
We also need to mention heteroreceptors. We talked about autoreceptors, which is a nerve listening to itself. Heteroreceptors are listening to the enemy.
Listening to the neighbors, at least. This is crosstalk. A sympathetic nerve terminal will often have muscarinic receptors on it. If a nearby parasympathetic nerve fires and releases ACI, some of that ACI can float over, hit the sympathetic terminal.
And do what?
And inhibit norepinephrine release. The G protein gets activated and shuts down the machinery.
So the vagus nerve can physically turn down the volume on the sympathetic nerve before the signal even reaches the heart.
Before it even gets to the effector. It's peripheral processing. It means the two systems aren't just shouting at the organ from opposite sides of the room. They are whispering to each other, coordinating the outcome in real time.
Which is so much more sophisticated.
Infinitely more.
Okay, section 6. Integration and system dynamics. This is the so what section. We've talked about molecules and receptors. Now let's talk about the patient sitting in front of you.
The first and maybe most important concept is tone. The autonomic system is never truly off. It's not dead silence. It is always humming in the background.
Give us a clinical example of why this matters so much.
The heart rate. The intrinsic pacemaker of the heart, the SA node. If you took it out of the body and put it in a dish, it would want to fire at about 100 to 110 beats per minute. That is its natural rhythm.
But I'm sitting here and my heart rate is probably 65 or 70.
Right. And why is that? It's because your vagus nerve is holding it back. You have high vagal tone. The parasympathetic brake is always slightly applied.
Okay.
Now, if I give you a drug like atropine, which is a muscarinic blocker,
I take my foot off the brake.
you take your foot off the brake, and your heart rate immediately shoots up to 100. Not because the atropine stimulated the heart, but because it simply removed the constant inhibitory tone that was already there. You can't predict a drug's effect unless you know the basal tone of the organ.
And conversely, the blood vessels have sympathetic tone. They are always slightly squeezed by the alpha receptors.
Exactly. So if you give an alpha blocker, they don't just stay the same. They flop open, your blood pressure plummets, and you might faint.
Right. It reveals the underlying tone.
It does.
Now, the final and most complex piece of the puzzle, the baroreceptor reflex. This is where students, myself included, always get tripped up. I call it the paradox of norepinephrine.
This is the ultimate test of your understanding of the whole system. Let's set the scene. You have a patient. You inject a bolus of norepinephrine intravenously. Based on what we just said about receptors, what should happen?
Okay, well, the direct action. Any hits beta-1 on the heart, so heart rate should go up. It hits alpha-1 on the blood vessels, so they squeeze and blood pressure goes up. Tachycardia and hypertension.
That is the direct pharmacological effect. That's what the drug wants to do. But if you actually watch the monitor, something strange happens. The blood pressure goes way up, but the heart rate slows down. You get bradycardia.
Why?
Because the body gets a vote. The body gets a vote. The baroreceptors in your carotid artery and your aorta sense that massive, dangerous spike in blood pressure. They panic. They scream to the brainstem, pressure is critical, we have to bring it down now.
And the brainstem's response is to do what?
To slam on the brakes. It activates the parasympathetic system. The vagus nerve fires aggressively, dumping acetylcholine on the heart to slow it down. And in this case, that reflex vagal action is so powerful that it completely overwhelms the direct beta-1 stimulation from the drug.
So the drug is pushing the gas pedal on the heart, but the brain is slamming the brake pedal even harder.
Much harder. The net result is high pressure, but a slow heart. And this teaches us the most important lesson in pharmacology. You cannot treat a drug as an isolated variable. You are introducing a perturbation into a homeostatic system.
And the system will try to cancel you out.
Every single time.
That is a profound place to land. We've gone from the synthesis of a single molecule all the way up to the integrated regulation of a vital sign.
It's the full loop, from molecule to organism.
Let's wrap this up. We have covered a massive amount of ground today.
We really have.
Yep.
We've looked at the 2-neuron relay, the snare zipper, the G protein cascades, and these complex reflex loops. It's a lot.
And if we look back at our mission synthesis, I think the big takeaway is that there are really only 7 pharmacologic intervention points, a sort of periodic table of neuropharmacology.
That's a great way to think about it. If you master these 7 mechanisms, you master the next 10 deep dives we do.
Let's list them. Number 1.
Synthesis. Block the factory, like using hemigalinium to stop HH production.
Number 2. Storage.
Block the loading dock. That's rizorpine stopping VMAT.
3. Release.
You can jam the zipper with Botox, or you can blow the door open with latrotoxin.
4 and 5 are the receptors.
Right. Receptor activation, where you mimic the key, like albuterol for asthma.
Right.
And receptor blockade, where you jam the lock, like with beta blockers or atropine.
It's his reuptake.
Jam the vacuum cleaner. That's cocaine and the tricyclic antidepressants.
And finally, number 7.
Degradation. Block the cleanup enzyme. That's what ACA inhibitors like neostigmine do.
Every drug we're going to talk about fits into one of those 7 buckets.
That's the playbook.
I want to leave the listener with one final, slightly provocative concept that I saw in the texts. Denervation supersensitivity.
Ah, yes. This is the idea of adaptation taken to its extreme.
What is it?
So we just said the body fights back. Well, what if you cut a nerve? Or if you use a drug like reserpine to deplete the signal for weeks on end, the target organ, like a muscle or a gland, doesn't just accept the silence.
It gets lonely.
It gets desperate. It starts synthesizing more receptors. It plasters its surface with new receptors, trying to catch even the faintest whisper of a signal that might come by.
It turns up the gain on the microphone to maximum.
All the way to 11. The tissue becomes exquisitely, dangerously hypersensitive. So if you suddenly stop the blocker drug, or if a tiny bit of transmitter leaks out,
boom, an exaggerated, explosive response.
This is the mechanism behind withdrawal syndromes. It explains rebound hypertension when you stop a drug like clonidine suddenly. You've created a monster by starving it of its signal.
The wiring isn't static, it is plastic. It changes based on how we treat it.
Precisely. The system is always learning.
Okay, that is it for the wiring diagram. I highly encourage you, if you're listening, to open Katsung Chapter 6 and look at Figure 6.3 for the cholinergic junction, and Goodman and Gilman Chapter 8 for the molecular details of that snare complex. The visuals really do solidify the concepts.
Absolutely. Reading the text is where the real retention happens. We've just tried to give you the hooks to hang all that detailed information on.
Thanks for diving deep with us. In our next session, we start putting these hackers to work on specific clinical problems. We'll see you then.
Stay curious.